Alright, so we're going to be solving some IB style questions in order to prepare you for the test that you have first class this coming week. And it's concerning the topics of sets, Venn diagrams, scientific notation, and approximation. Let's look at number 1. We've been given these four numbers, 5, 0.5, the square root of 5, and negative 5. And we need to determine which number sets they belong to. So first let's just look at some terminology. The n, that means the natural numbers. And you can think of those as 0, 1, 2, 3, 4, etc. Okay? The real numbers, that's everything. Every imaginable type of number that you will ever see in this course, no matter how strange the number looks, it will be a real number. And Q means the rational numbers, and the rational numbers, Q, these are the numbers that can be expressed as fractions. And they can also be expressed as decimals as long as the decimal either stops, doesn't go on forever, or some part of the decimal repeats again and again and again forever. And so if a rational number, if a fraction is expressed as a decimal, one of those two things is bound to happen. Alright, here we go. So let's look at the number 5. Well, that is in the simplest set of numbers at 0, 1, 2, 3, 4, 5, so it is a natural number. And we know that everything is a real number. For that matter, I may as well just put 3 ticks and fill in the entire real column, because every number we see will be a real number. I suppose actually, now that I think about it, I can think of one exception. I suppose if you had like a number like infinity, that's actually not a real number. Infinity is more of a concept. And something with a denominator of 0 we know is undefined. And if it's undefined, well then I guess it's not a real number either. But I mean, these are very rare things. You're probably going to be dealing only with real numbers throughout the course. Let's look at the next number, 0.5. Can we see it's not a natural number because it's not a whole number. But of course it's real. Can we express it as a fraction? We certainly can. In fact, I can demonstrate this on the calculator by typing in 0.5. And then I'll take my answer and I'll go math, and you see how fract is already, I'm going to express my answer as a fraction. So this is the answer to the previous thing I did in the calculator. Let's express it as a fraction if possible. Yes, it is possible. It gives me 1 over 2. That's evidence that 0.5 can be expressed as a fraction. How about the square root of 5? We already know it's not a natural number, but of course it's real. Is it a fraction? So I'm going to take now the square root of 5 on my calculator, and let's convert this. Now, this should tip you off already. Look at this decimal. It goes on forever with no apparent end in sight. It simply ran out of room on the calculator's display. And so it's going on forever. Can you see any repeating part? I can't see any pattern that is very apparent it's going to continue forever. We don't have enough evidence of a repeating decimal. And as a result, it must be an irrational number. It can't be expressed as a fraction. But another argument would be to say, let's convert this decimal number into a fraction and see what happens. It couldn't do it. And so clearly root 5 is not a rational number. And lastly, the negative whole number of 5. That's not a natural number. The natural numbers only deal with the positive numbers and 0. This is a negative number, so it doesn't count as natural. It is an integer, by the way. Just a side note. But it is not a natural number, because these are going to be positives. Or maybe it's better to say non-negatives. Or non-negative wholes. How's that? So that's a good way of thinking about the natural numbers. Alright, and the last one to fill in is negative 5 expressible as a fraction? Well, of course, we can put any integer whatsoever over 1. And so yes, it can be expressed as a fraction. And so we'll just have a quick look at the mark scheme. This is worth a total of 8 marks. And I assume it's because we had to fill in 8 different spots. 1, 2, 3, 4, 5, 6, 7, 8. And so we'll just check our work. We're expecting that we have 3 check marks across the top. The last 2 are check marks in the second line. Same with the 4th line. And the 3rd line has only got a check mark in the middle. Let's just check that out. Oops. There we go. Yes, all check marks, the last 2 in the 2nd and 4th, and only the middle one. And of course these are all worth 1 mark each to give you a total of 8 marks. Alright, here we go. Next problem. Number 2. Now that we've done a little review of what the number sets are, maybe I can go a little bit quicker through this problem. We need to write all of these numbers into this Venn diagram. And so the inner circle are the natural numbers. And that's the smallest group of numbers because it includes only the positive or non-negative wholes. So let's just look through the list. Can you see any such numbers? Yeah, the 1. So the 1 is the only number that goes in the middle. Let's now move to the next circle outward. I always like to go from inside out when I'm dealing with Venn diagrams. And so Z represents the set of integers. Do we have any integers that I haven't already counted? I mean, my 1 is safely in the circle of integers because n is a subset of Z. Any other integers? Yes, I can see this one here, -1, so it belongs in that circle. Alright, no other integers. Which of the remaining numbers are rational numbers? Well, clearly 7 over 16 is expressible as a fraction. It's being expressed as a fraction. Let's have a look at, say, 3.33333. Ooh, and that 3's got a dot over it, meaning that the 3's go on forever. Although this is a decimal that goes on forever, it's clearly got a repeating segment to it. And when you have a decimal that goes on forever with a repeating segment, that means that it can be expressible as a as a rational number, a fraction. In fact, 3.333333 would be the same as 3 1/3, which you could express as 10 over 3. Alright, so we've handled these two, and let's look at pi and square root of 3. I already happen to know that square roots of anything, if I had a square root of a whole, like a nice square number like that, sure. Alright, you end up getting, not only is it a rational number, but it's also an integer, and it is a natural number. But the square root of non-perfect squares, like square root of 3, that doesn't come out nicely to a perfect integer. Automatically, I know that it is going to be irrational. I can convince you of this maybe by doing the square root of 3, and then I'll immediately convert this into a fraction, and you'll see that it can't. It leaves it as a decimal. And also, pi, you might know already, cannot be expressed as a fraction. A little bit of evidence of that. Let's try to express pi as a fraction, and it is unable to, leaves it as a decimal. So pi must also come out here. Let's just check the mark scheme and see if we placed these 6 numbers in the right place. So that's 2 on the outside, 2 in the next circle inwards, and then 1 in the 2 inner sets. And sure enough, there's the pi and the root 3, there's the fraction and the repeating decimal, and then here are the other 2 numbers on the inner subset circles. Moving on to number 3 now. The universal set has been given with, looks like 8 different values inside. It says that set A is the integers and B will be the rational numbers, so I guess those are going to be subsets. Part A, list all the prime numbers contained in the universal set. Prime numbers. Prime numbers are a subset of the natural numbers because only positive numbers can be considered as prime, and the definition of a prime number is a number with exactly 2 factors. There's only 2 things, and those be exactly only 2 things by which it can be divided, which is usually, well, which is always 1 and itself. For this reason, 1 is not a prime number. Look, I understand that 1 can only be divided by 1 and itself, but those 2 numbers are the same. That means that 1 has only got 1 factor, 1, while the smallest prime number of 2 has got 2 factors, 1 and 2. And so the definition of a prime number, any positive integer with exactly 2 factors. And so as we look through this set, this is a negative, that's a fraction, that's the 1, we know that's not prime. Here we go, 13, that's a prime number. And 69 can be, sorry, this is of course not prime because it's a decimal. 69 is divisible by 3. It's 3 times 23, so it's not prime. 10 to the power of 33. Imagine moving the decimal over 33 times, this huge long number with 33 zeros. Well, because it's got a 0 at the end, it's obviously divisible by 10. So the only prime number that we have here is 13. Part B, list all the members of A. So that's going to be the set of integers, and that of course will include that 13, but I've got a negative whole number here, negative 4, and I can see now my 1, and we already mentioned the 13, and then 69 is an integer because it's got no decimal part, and 10 to the power of 33, if I wrote it in regular notation, would also have no decimal part afterwards. So those are the 5 integers. B is the set of all the rational numbers. So anything that can be expressed as a fraction. Well, then we've got negative 4, because I could write that as negative 4 over 1. I've got negative 2 over 3. I've got, well, pi, we've already agreed in an earlier question, cannot be written as a rational number, as a fraction. So we'll have to skip that one. 13 I can write as 13 over 1. Now have a look at 26.7. It's a decimal number that terminates. It doesn't go on forever. So automatically, I know that it can be expressed as a fraction. And I think the calculator can demonstrate this for us. If I did 26.7, converted it into a fraction, and, come on calculator, think about it. There we go, it's 267 over 10. 69 can obviously be expressed as a fraction, 69 over 1, and 10 to the power of 33. If I wrote it in standard notation with 33 zeros, I can just write that big old number all over 1. So yes, it can be expressed as a fraction. Part D, list all the members of the set A and B. That is to say, what numbers belong to both sets, both A and B at the same time. So I look for the common overlapping elements. We've got negative 4. 1 does not appear in both. Negative 2/3 does not appear in both, but 13 does. 26.7 doesn't appear in both, but 69 and 10 to the 33 do. Those are our common elements that appear inside both circles, set A and set B, and thus they are the members of the set A intersection B. Whoops, let's just check the mark scheme on this. So it's 2 marks for each of A, B, C, and D. See, I've got just a single value of 13 up in part A, and then I've got these 5 values in part B. Let's just check those. So the only prime number, it says, for part A is 13. Great. And these are the 5 values that I had for part B. Okay. Set B, which is part C in the question, has got 1, 2, 3, 4, 5, 6, 7 of the 8 elements. In fact, the only one it's excluding is pi, and that's indeed what we have in our solution. Okay, 1, 2, 3, 4, 5. Ooh, did I miss one? Oh, yeah, if you had all been in here in class, I'm sure you would have said something to me. My fault. I've got to change my solution here, don't I? I made a mistake. It looks like the one I missed out was 1. There's this element here that I somehow missed, and so that is of course also expressible as an integer, a rational number, 1 over 1. And this gives us then an additional thing which exists in both sets A and B. So I end up with 5 elements in the intersection. So, whoops, I guess I don't get full marks. 1, 2, 3, 4, 5. There we go. And we finished question number 3.